Fire a single electron at two slits, and it passes through both at once. That sentence should be impossible. Physics has known this for 100 years, and it has never recovered. Every interpretation that followed leads somewhere worse, a universe that only snaps into existence when someone looks at it, a past that gets written after the fact, and an observer who is made of exactly the same uncertain stuff as the particle under the microscope. The deeper you push into the logic, the more the solid world around you becomes a question. Understanding this only deepens the dread. It makes you part of the paradox. If you want to go there, subscribe, then brace yourself. We begin. In a quiet laboratory, a physicist fires electrons through a screen with two small slits, one at a time. Single electrons, each one alone. There is nothing for them to interfere with. And yet, after firing hundreds of them and waiting to see where they land on a detector wall behind the slits, something impossible accumulates. An interference pattern. The kind of pattern you would expect from waves passing through two openings and overlapping on the other side. The kind of pattern you would get if you dropped two stones in a still pond and watched the ripples cross each other. Bands of impact. Bands of emptiness. An alternating rhythm of hits and gaps that can only emerge when two waves are interacting. There was only one electron at a time. There was nothing to wave. There was nothing to interfere. Physics has spent nearly 100 years staring at this result and has never fully recovered. The double-slit experiment was first performed with light in 1801 by Thomas Young, who used it to prove that light behaves as a wave. That was strange enough. But in the 20th century, physicists began sending quantum particles through the same setup. Electrons, atoms, eventually molecules. All of them built up the same pattern. All of them behaving as if each individual particle had somehow passed through both slits simultaneously, as if each one split into a wave, threaded through both openings, interfered with itself on the other side, and then arrived as a single particle at a precise point on the detector. The math backs this up completely. Quantum mechanics says each electron, until detected, exists as a wave of probability spreading out through space. It passes through both slits. It interferes with its own probability. The interference pattern is the fingerprint of that self-interference, written on the detector screen one electron at a time. Here is the part where the story turns. Ask a quantum physicist what is actually happening when the electron goes through, and the most honest answer you will ever get is this: nobody knows. Richard Feynman, one of the most brilliant physicists who ever lived, told audiences for decades, "I think I can safely say that nobody understands quantum mechanics." He was being precise. The pattern on the screen is real. The mathematics predicts it exactly. And the mechanism, the actual physical story of what the electron is doing while it travels, remains one of the deepest unsolved problems in the history of science. A gap at the foundation of reality. The experiment has been repeated thousands of times with increasingly careful controls, with every type of quantum particle, in laboratories on every continent. The result never changes. The interference pattern always appears. And every time it does, it quietly announces something the equations confirm but human intuition still refuses to absorb, that a single particle, alone in space, has no single path. That before it arrives somewhere, it effectively exists everywhere as a smear of possibilities. That the universe, at its smallest scales, is made of things that are probabilities rather than objects. This is where physics stands. This is the wound. And what happens when you try to look closer? When you install a detector and actually watch which slit each electron uses, turns out to be far more disturbing than the pattern itself. Physicists are not satisfied with mysteries. They probe them, so the natural next step after discovering the double-slit interference pattern was to find out what was actually happening. Simple enough. Install a detector near the slits. Watch which one each electron goes through. Record the path. Understand the mechanism. The experiment was done. The detector was installed. The electrons were fired. The interference pattern disappeared. Completely, instantly, without ambiguity. The moment the detector was in place and capable of recording which slit each electron passed through, the alternating bands collapsed into two plain blobs, exactly where you would expect if the electrons were behaving like ordinary particles, each one taking a single path, each one choosing left or right. Turn off the detector, and the interference pattern comes back. Switch it on again, and it goes. The first interpretation physicists reached for was the most intuitive one. The detector must be disturbing the electron somehow. Measuring something delicate requires touching it, and touching it changes it. The measurement disturbs the path. The interference is destroyed. Simple. This explanation does not survive inspection. Experiments have been designed where the detector was made so sensitive and so gentle that any physical disturbance it could introduce was far too small to change the electron's path in any meaningful way. The interference pattern still disappeared. Then physicists built detector arrangements that did not interact with the electrons at all, devices technically capable of recording which path information, but that never actually triggered, never fired, never left any record. Arrangements where the potential for information existed, even if no information was ever written down. The interference pattern still disappeared. The universe does not respond to the physical disturbance of the measurement. It responds to the capacity for knowledge. If something in the experimental setup is theoretically capable of recording which path the electron took, even if it never does so, even if the record is never created, the interference vanishes. The universe appears to care whether it can be watched, and it responds accordingly. Niels Bohr spent decades wrestling with what this means and concluded that quantum systems simply do not have definite properties independent of measurement. The electron does not travel a path. The question, which slit did it go through, has no answer until something forces one. When you make such an answer possible, you make a definite path real. And a definite path and an interference pattern are mutually exclusive. You cannot have both at once. The larger implication, the one most people walk past too quickly, is this. The electron's path is created by the act of looking, not discovered by it. What you find when you measure is something that exists because you measured. Looking at reality does not reveal it. Looking at reality produces it. Bohr himself said that if quantum mechanics has not profoundly shocked you, you have not understood it yet. Physicists have spent a century debating what this means. They have never agreed. What they have agreed on is that the mathematics is exact, the experimental results are unambiguous, and the underlying story of what is actually happening remains, stubbornly, missing. The equation that governs all of this is the Schrödinger equation, and it is one of the most successful pieces of mathematics in history. It predicts everything correctly, and it contains, hidden in its perfect machinery, a problem that has never been solved. Physicists will tell you this sincerely, the way musicians describe a perfect chord. Feed it a quantum state at any moment in time, and it tells you exactly how that state evolves forward. Feed it the state of an electron before it reaches the double-slit screen, and it will give you, with perfect accuracy, the spread of probabilities for where the electron will land. It has been tested against experiment more times than any other equation in physics, and it has never been wrong. Here is the problem. The equation describes a quantum system evolving in superposition, a spreading wave of possibilities expanding continuously through space. It never narrows that wave down to a single point. It never selects one outcome from the many. It describes a world of perpetual smear, perpetual overlap, perpetual both at once. But when you make a measurement, you get one answer, one position, one spin, one definite click of the detector. The superposition vanishes. The probability wave appears to collapse instantly into a single point, leaving behind exactly one result. The Schrödinger equation does not contain this collapse. There is no moment in the equation where the smooth, spreading wave function sharpens into a single outcome. What physicists do is add it by hand, as a separate rule bolted onto quantum mechanics from outside its own mathematics. They call it the Born rule, named after Max Born, who proposed in 1926 that the probability of finding a particle at any given location is proportional to the square of its wave function at that location. Take the wave, square it. That is your probability. When a measurement happens, one of those probabilities wins, and the rest vanish. This works. The predictions are exact. Generations of physicists have used the Born rule to build semiconductors, lasers, magnetic resonance imaging machines, transistors, and everything else in the modern world. The rule is correct. It has also never been derived from the Schrödinger equation. It is an instruction physicists follow because following it gives right answers, and no one has explained why it works or what it actually means. The philosopher of physics Tim Maudlin put it plainly: the measurement problem is not solved, and it is not even clearly posed by most physicists. The engine of quantum mechanics runs without a fault, and at the exact moment, it should explain what happens when a measurement is made. When the smear becomes a point, the theory is silent. It tells you the odds. It does not tell you what happens. This gap has a name: the measurement problem. It has been sitting at the center of quantum mechanics since the theory was formalized in the 1920s. Every generation of physicists has tried to close it. Every attempt has either introduced untestable assumptions or created new paradoxes worse than the one it was meant to solve. 100 years of extraordinary experimental success has, in a strange way, made the problem more urgent. The more precisely physicists confirm that quantum mechanics is correct, the more pressing the question of what it is actually saying about reality becomes. The equation is exactly right. The interpretation is missing. The most successful theory in the history of science is, at its foundation, a set of instructions for calculating results from a process nobody understands. That gap is where the horror begins. And the man who pointed at it most clearly did so with a sealed box and a cat that was, until someone looked, both alive and dead at the same time. Erwin Schrödinger was brilliant, and he was annoyed. The year was 1935, and the Copenhagen interpretation, which Niels Bohr and Werner Heisenberg had spent years constructing as the dominant framework for quantum mechanics, had established something that Schrödinger found philosophically intolerable: the superposition of quantum states. The idea that a particle could be in multiple conditions simultaneously until observed was being treated as a complete and satisfying description of reality. Schrödinger thought this was absurd, and he designed a thought experiment to demonstrate why. Imagine a sealed box. Inside, a cat, a small amount of radioactive material, a Geiger counter, a vial of poison, and a mechanism connecting them. If the Geiger counter detects a radioactive decay event, the vial shatters and the cat dies. The radioactive material has a 50% chance of producing a decay event within 1 hour. After 1 hour, before the box is opened, quantum mechanics describes the radioactive atom as being in a superposition of both decayed and undecayed states simultaneously. The Geiger counter is connected to the atom. The poison is connected to the Geiger counter. The cat is connected to the poison. The Schrödinger equation, applied to the entire system, says the whole thing is in superposition. The atom is both decayed and undecayed. The vial is both intact and broken, and the cat is both alive and dead at the same time. Schrödinger did not believe this. He wrote the thought experiment to expose what he called the quite ridiculous consequence of applying quantum rules to everyday objects. The cat cannot literally be in two states at once. Something was wrong with the interpretation. The physics community's response over the following decades was to absorb the absurdity and continue calculating. The Copenhagen interpretation handles this by saying the superposition collapses when an observation is made, but it refuses to define precisely what counts as an observation. Does the Geiger counter collapse it? Does the air inside the box? Does the cat itself, through its own biological processes? Does the scientist opening the lid? The founders of the interpretation left this unspecified. Bohr essentially argued that asking what the cat's state really is before observation is not a valid scientific question. This answer satisfied enough physicists to keep the field moving forward. But it left behind a question that has never been quieted. Where exactly does the quantum world end and the classical world begin? At what scale does superposition stop being a real physical condition and become merely a representation of human ignorance? This boundary is called the Heisenberg cut, after Werner Heisenberg, who acknowledged it must exist somewhere without specifying where. Every interpretation of quantum mechanics hides this cut somewhere. Every one of them hides it in a different place, and none of them have ever identified it physically because the Schrödinger equation draws no such line. For decades, the cut could be safely assumed to live somewhere in the gap between subatomic particles and everyday objects. The gap was vast enough that the ambiguity felt harmless. Then laboratories began pushing objects into quantum superposition, bigger ones. And each time technology advanced, the boundary moved. And no one could find a reason for it to stop. For most of the 20th century, quantum superposition was a phenomenon that happened to things too small to think about in ordinary terms. Electrons, photons, atomic nuclei. The quantum world and the everyday world were separated by an enormous practical gap. The Heisenberg cut might be philosophically imprecise, but it was comfortably far away from anything you could see or touch. Then the experiments started crossing the gap. In the 1990s, physicists in Vienna began placing increasingly large molecules into superposition. They fired molecules through double slit-style gratings and found that even large organic molecules, containing dozens of atoms, produced interference patterns. The molecules were behaving as quantum waves. By 2019, a team in Vienna had placed molecules containing nearly 2,000 atoms into quantum superposition, observing genuine interference effects from structures large enough that calling them subatomic was almost misleading. These were small but real molecular assemblies, existing in multiple paths simultaneously. Then, researchers achieved superposition of a vibrating mechanical resonator, a tiny metal beam visible under a microscope, cooling it to its quantum ground state and placing it in a superposition of two distinct vibrational modes at once. The object could be seen with standard laboratory optics. It was quantum. Each of these experiments pushed the Heisenberg cut further back, closer to the scale of everyday life. Every time technology improved and isolation from environmental disturbance became more precise, the size limit for quantum behavior moved upward. There was no natural stopping point anywhere in sight. Some physicists began to argue there is no stopping point. The Heisenberg cut might be a feature of decoherence, the process by which quantum superpositions become scrambled when a system interacts with its surroundings, rather than a feature of nature itself. Decoherence happens extremely fast for large objects because large objects interact with trillions of environmental particles per second. Air molecules, photons, vibrations, all of them constantly interacting with the object in a way that scrambles its quantum coherence in timescales shorter than any instrument can track. A large object appears classical because its quantum superposition leaks away into the environment faster than any lab can follow. But leaking away into the environment is different from ceasing to exist. The superposition does not end. It spreads. It entangles the object with its surroundings. From the inside, the coherence becomes invisible. From the outside, from the perspective of a sufficiently large and isolated observer, the combined system of the object and its environment remains in superposition. This means the Heisenberg cut does not cleanly divide quantum from classical. It divides what we can access from what we cannot. The classical world is the quantum world viewed from inside, with quantum coherence rendered invisible by the scale and speed of environmental entanglement. Follow that logic one step further, and you arrive somewhere very uncomfortable. If there is no true boundary between quantum and classical, and if the Schrödinger equation applies to all physical systems without exception, then the atoms in your body, the neurons firing in your brain, the decisions you feel yourself making right now, all of these are, in principle, quantum systems, capable of the same superpositions. You are not observing the quantum world from the outside. You are inside it. Take a moment to sit with what the last argument actually implies, because it is easy to let it slide past without feeling its full weight. If the Schrödinger equation applies without exception, and if the Heisenberg cut is a feature of our limited vantage point rather than a feature of nature, then the following becomes true. You, as a physical system made of atoms governed by quantum mechanical laws, are subject to superposition from the perspective of any observer who has not yet interacted with your quantum state. You are Schrödinger's cat. The box just has not opened. In practice, you do not feel this way. Your experience is continuous, definite, single. You are somewhere specific right now, thinking specific thoughts. The quantum fuzziness governing electrons appears nowhere in your moment-to-moment experience of being a person. For a long time, this gap between the quantum description and lived experience was explained away by pointing to decoherence. You are so thoroughly entangled with your environment that your quantum superposition decoheres instantaneously into something that looks and feels entirely classical. But here is the issue. Decoherence explains why quantum coherence becomes invisible from inside the system. It does not explain why a single definite outcome occurs. An observer who has not yet interacted with you, standing outside your decoherence environment, applying the Schrödinger equation to the combined system of you and your surroundings, would still describe you in quantum superposition. The equation says you are. Your experience says you are not. The theory has no rule for choosing between these two descriptions. The physicist who pressed hardest on this point did it in 1961, and the thought experiment he created was so precise and so uncomfortable that the physics community spent decades explaining why it could not possibly be real. Then a laboratory in Edinburgh made it real. His name was Eugene Wigner, and he invented his thought experiment to illustrate a specific and troubling gap in the theory. The fact that two observers, each applying quantum mechanics perfectly and correctly from their own perspective, can arrive at irreconcilable descriptions of the same physical event. Wigner was a Nobel laureate, one of the architects of quantum mechanics, a man who had spent his career pushing the formalism to its limits. He spent the later years of that career quietly convinced that something had been missed, that the theory he helped build was incomplete in a way that touched something deeper than the measurement problem. The question of what a fact actually is when the universe is governed by quantum mechanics. His thought experiment begins with a sealed room and a scientist inside it. The scientist measures a quantum particle. She gets a result. She has a fact. Outside the room, a second observer applies the Schrödinger equation to the entire sealed system. And that second observer's mathematics describes everything inside, including the scientist and her fact, as still being in quantum superposition. One of them is holding a reality, the other one is not. The theory cannot say which one is right. What makes this worse is that both of them are correct. Here is Wigner's scenario laid out precisely, because the details matter. A physicist, call her the friend, is sealed inside a completely isolated laboratory with a quantum particle. She measures the particle's polarization. The polarization can come out one of two ways, and she gets one of them. From inside the lab, the quantum measurement has occurred and produced a single, clear outcome. Vigna stands outside the lab. He cannot communicate with her. He cannot receive any information about what happened inside. From his perspective, using the Schrödinger equation to describe the entire isolated system, including the particle, the measuring device, the lab, and his friend, the system is in superposition. Two possible outcomes exist. Neither has collapsed. Nothing inside the lab, from his mathematical perspective, has resolved into a single fact. Both Wigner and his friend are applying quantum mechanics correctly. Both are following the same theory. Both are doing the math right. His friend has a definite outcome. Wigner has a smear of possibilities. They are describing the same physical moment. The descriptions do not agree, and quantum mechanics provides no rule to determine which description is the more accurate one. Wigner himself, when he first published this thought experiment in 1961, used it to argue that consciousness must play a special role in quantum mechanics. His friend's conscious observation collapsed the wave function, he suggested, and Wigner's description was simply ignorance of a result that had already, in some physically meaningful sense, occurred inside the lab. He later walked back this interpretation, acknowledging it introduced more problems than it solved. The physics community's dominant response for the following decades was practical. The scenario is imaginary. You cannot actually put a human being in quantum superposition. The friend's brain interacts with so many environmental particles so quickly that any coherent quantum description of the combined lab system would decohere on timescales so short they were physically meaningless. The thought experiment was never going to be physically realized, so it was a puzzle to entertain theoretically, not a crisis to resolve experimentally. This response was comfortable for 58 years. In 2019, a group of researchers at Heriot-Watt University in Edinburgh built an experiment where the role of the friend was played by a pair of entangled photons acting as quantum measurement devices, and the role of Wigner was played by external observers capable of measuring whether the friend systems were still in superposition. They ran the experiment and tested whether objective, observer-independent facts could survive. They tested a version of Bell's inequality adapted for the Wigner's friend scenario, an inequality that must be satisfied if measurement outcomes are objective facts that exist independently of who is observing. The inequality was violated. The conclusion, written in the paper by Massimiliano Proietti and his team, was careful and unambiguous. Quantum theory cannot be described by a single, objective reality. Different observers, each applying quantum mechanics correctly from their own position, reached genuinely irreconcilable descriptions of the same physical event. A thought experiment that the field had been comfortable calling impossible had just been run in a laboratory, and it was about to get considerably worse. Take a moment to absorb the weight of what that Edinburgh experiment actually found. The experiment was not showing that observers have different information and therefore reach different conclusions, the way two people watching a match from different angles might disagree about whether a ball crossed a line. Different vantage points, same underlying event, reconcilable with more information. The experiment was showing that the descriptions produced by the two classes of observers are fundamentally irreconcilable, a structural feature of how the theory works rather than a consequence of limited information. The friend holds a definite result. The external observer's quantum description of the lab assigns probabilities to multiple outcomes, including the friend's definite result, as if it has not happened yet. Wigner can call his friend on a phone and ask, "Did you get a result?" The friend can answer, "Yes, I got a definite result," without revealing what it was, and Wigner's mathematical description of the lab remains completely unchanged. He is still describing a superposition. She is still holding a fact. When Wigner then performs his own measurement on the lab system, He gets a result that is consistent with his description. The friend, informed of Wigner's result, finds that it is consistent with hers. Nobody detects a contradiction directly. The violation of the inequality is only visible when you aggregate statistics across many runs of the experiment and check whether the correlations between what friends observe and what Wigners observe satisfy the constraints any objective, observer-independent reality would have to obey. They do not. The correlations are quantum correlations. The only way to make sense of the data is to accept that. At the quantum level, the concept of a single objective fact, something true independent of which observer you ask, breaks down. The physicists who ran the experiment listed the possible conclusions clearly. Either quantum mechanics is wrong and some new physics is needed, or measurement outcomes accessible to one observer can genuinely be inconsistent with those accessible to another, with no deeper layer of reality reconciling them. Every option was deeply uncomfortable, and this experiment was only testing a simplified version of the paradox, using photon systems as stand-ins for human-like observers. A year before the Edinburgh result, two theoretical physicists had gone further. Using nothing but quantum mechanics' own rules, they had proven that the theory produces an outright logical contradiction. The title of their paper said it plainly. Quantum theory cannot consistently describe the use of itself. Albert Einstein spent the last decades of his life fighting quantum mechanics, and not because he was confused or out of touch. He understood it better than almost anyone. What he could not accept was what it seemed to be saying about the nature of reality. In 1935, Einstein worked with Boris Podolsky and Nathan Rosen to construct an argument that has come to be known as the Einstein, Podolsky, and Rosen paradox. The argument was about what happens when two particles interact and then separate. When two quantum particles interact in the right way, they become entangled. Their quantum states are linked by a single shared wave function. After they separate, even if they travel to opposite sides of a room or opposite sides of a galaxy, measuring one of them instantly determines the outcome of measuring the other. Measure one particle's spin and find it pointing up. And its entangled partner, no matter how far away, will immediately be found pointing down when measured. Einstein recognized this implication and called it spooky action at a distance. His objection was not to the experimental observations. It was to the interpretation. Either quantum mechanics was implying some kind of instant influence between particles regardless of distance, which violated special relativity, or the two particles were never really in an uncertain state to begin with. They must have carried predetermined answers with them all along, values that quantum mechanics had simply failed to describe. He called these predetermined answers hidden variables. If hidden variables exist, then quantum mechanics is like classical statistical mechanics, a useful way of describing probabilities over a deeper, definite reality we have not yet mapped. The universe would still be the sensible, determined, local place that Einstein's intuitions demanded. Einstein spent the rest of his life convinced that a complete theory was waiting to be found, one that would reveal the definite values beneath the quantum smear. He died in 1955 without it. 9 years later, an Irish physicist named John Stuart Bell found a way to test whether Einstein's conviction was correct. Bell was a staff scientist at a European particle physics laboratory working on accelerator design. He published his paper in a low-circulation journal because the mainstream physics community did not consider foundations questions important enough for major publications. His paper sat largely unread for years. It was also one of the most important things ever written about the nature of physical reality. Bell showed that the question of whether hidden variables exist is a mathematical question, with an experimental answer. He derived specific numerical limits on the correlations between measurements of entangled particles that must hold if any hidden variable theory is correct. If the observed correlations exceed those limits, hidden variables cannot exist. The universe itself would have ruled them out. The assumptions behind Bell's inequalities seemed almost too obvious to name. That causes precede effects. That measuring one particle cannot instantly influence a physically separated particle, and that the experimental setup is free from prior causal conspiracies. These were the minimum requirements for calling the universe sensible. Bell's theorem meant that whether the universe is sensible, in Einstein's sense of the word, was now a question that an experiment could answer. John Clauser was a graduate student at Columbia University when he first read Bell's paper in the late 1960s. Most physicists at the time considered it a theoretical curiosity with no practical implications. Clauser thought it was the most important question in physics. He spent years trying to get funding and institutional support for an experiment to test it, and spent years being told that quantum foundations was not serious research. He ran the experiment anyway, in 1972, with his colleague Stuart Friedman. They entangled pairs of photons and measured their polarizations along different angles, checking whether the correlations exceeded Bell's inequality. The inequality was violated. The correlations were too strong for any hidden variable theory to explain. Quantum mechanics predicted them exactly. There were loopholes. The detectors in Clauser and Friedman's experiment had low enough efficiency that one could argue the photons being detected were a biased sample. And the two detectors were close enough together that one could not rule out a signal traveling between them during the measurement, allowing one particle to know how the other was being measured. These were the detection loophole and the communication loophole, and they were genuine escape routes for anyone wanting to preserve hidden variables. A French physicist named Alain Aspect closed the communication loophole in 1982. He designed an experiment where the detector settings were switched randomly while the photons were in flight, after they had already left the source. Any signal attempting to coordinate the two measurements would have had to travel faster than light. The inequality was still violated. The experiments kept coming, and each one closed another gap. By the 1990s, quantum entanglement had been demonstrated over distances of more than 100 miles. By the 2000s, the experiments were so refined and the violations so consistent that hidden variables had become untenable to all but a small number of physicists willing to accept increasingly baroque alternatives. One final cluster of loopholes remained: the detection loophole, the freedom of choice loophole, and the communication loophole had never all been closed simultaneously in a single experiment. In 2015, 3 independent groups did exactly that. A team at Delft University in the Netherlands, a team at the National Institute of Standards and Technology in Boulder, Colorado, and a group in Vienna. All 3 ran their experiments within the same year. All 3 found the same result. Bell's inequality was violated. Hidden variables do not exist. The Delft experiment was particularly decisive. It used entanglement over a distance of more than 1,200 feet, with detection efficiencies high enough to close the detection loophole, and with measurement timing sufficient to close the communication loophole. The settings for each measurement were chosen by a quantum random number generator, closing the freedom of choice loophole. The inequality was still violated. This might seem like a settled question. 3 simultaneous experiments, all loopholes closed, same answer from different teams on different continents. But there was still one imaginable escape. The random number generators used to choose the measurement settings were generated by events happening on Earth, in the same era as the experiment. What if some ancient, pre-arranged cause had set up both the experimental settings and the particle's behavior in advance? In physics, a possibility that has not been experimentally eliminated is a loophole that exists. So someone closed it too, with light from dead stars. The freedom of choice loophole is the strangest escape hatch in physics. It says, perhaps the particles knew in advance how they would be measured and arranged their hidden properties accordingly, because some common cause in the distant past determined both the measurement settings and the particles' behavior simultaneously. The particles and the detectors were never truly independent. The experiment was never truly free. To eliminate this, you would need measurement settings chosen by something completely causally disconnected from the particles being measured, something so far removed in time and space that no common past cause could have influenced both. You would need a source of randomness that predates the experimental setup by a sufficient margin that no conspiracy could have coordinated them. In 2018, a team led by Anton Zeilinger in Vienna decided to use the universe itself. They designed what became known as the cosmic bell test. Instead of using quantum random number generators to choose measurement settings, they used light from distant quasars, some of the oldest and most distant objects in the observable universe. The measurement settings at each detector were determined by the color of incoming photons from quasars that emitted their light billions of years before our solar system formed. The logic was precise. If any hidden mechanism was exploiting the freedom of choice loophole, it would have needed to set up its influence before that quasar light was emitted. It would have needed to arrange, billions of years in advance, both the properties of entangled photons in a Vienna laboratory and the color of light from galaxies that had no knowledge of human experimenters. If such a mechanism could thread that needle, it could explain everything. If Bell's inequality was still violated, then hidden variables were ruled out even from this extreme scenario. The experiment was run. Bell's inequality was violated. The correlations between the entangled photons exceeded the limits for any hidden variable theory, even one with a billion-year head start. The universe had no hidden depths at any scale, across any distance, at any point in its history. The Nobel Committee agreed. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their experiments testing Bell's inequalities and establishing entanglement. The Nobel Committee's language was unambiguous. Quantum particles have no definite properties before measurement. Definiteness is created by the act of measuring, not revealed by it. The universe does not commit to specific values until something forces it to. This is the settled conclusion of decades of experimental work and the considered judgment of the Nobel Committee. The universe is, at its foundation, indefinite. Reality does not exist before observation. Einstein was wrong. Now, sit with the next question. If particles have no definite properties before they are measured, and measurement creates definite values rather than discovering them, then what counts as a measurement? What is the observer that turns quantum possibility into classical fact? And what happens when that observer is itself a quantum system? Because two physicists had already built a scenario where those questions rip a hole in the center of the theory. A hole from which no interpretation of quantum mechanics has yet escaped. The Nobel Committee's verdict landed with unusual precision for a prize in physics. There are no hidden variables. Quantum particles have no definite properties before they are measured, and definiteness is created by observation rather than revealed by it. This was the conclusion of 50 years of Bell tests, carried through increasingly airtight experiments until no reasonable escape remained. It is now the settled foundation of the field, but the verdict left something unanswered that is, in some ways, more unsettling than the conclusion itself. When two entangled particles are measured and their outcomes are found to be correlated in ways that violate Bell's inequality, what exactly is happening between them? The popular description, spooky action at a distance, makes it sound like a signal travels between the particles, a kind of quantum telephone call alerting one particle to what happened to the other. This description is wrong in a way that matters enormously. Entanglement is not a signal. Nothing travels between the particles. You cannot use entanglement to send information faster than light because the outcome of your measurement appears random. Your entangled partner gets a correlated random result, but neither of you controls what that result will be, and so there is nothing to transmit. Relativity is not violated, but what is happening is stranger than any signal would be. When two particles are entangled, they are described mathematically by a single wave function. They are not two objects with a relationship between them. They are one object, extended across space. That appears to be two things only because we encounter it at two locations. The quantum state is genuinely unified, genuinely non-local, genuinely indifferent to the distance between the points where measurements are made. Space does not cut the connection because the connection was never carried by space to begin with. Two photons are produced in a laboratory. They travel in opposite directions for miles. And when you measure the polarization of one, its partner shows a correlated polarization instantly, regardless of the distance. Einstein's deepest intuition, that physically separated objects must have independent properties, turns out to be simply false. The universe does not honor the independence of distant things. At the quantum level, objects can be unified across space without any signal crossing that space, without any physical process doing the connecting, because separation is something that happens in classical descriptions of reality rather than in quantum reality itself. The experiments at the Large Hadron Collider in 2024 push this further. Physicists confirmed quantum entanglement between top quarks and their antiparticles, the heaviest known fundamental particles, existing for less than a trillionth of a second in the most violent collisions humans have ever produced. These particles, formed at energies trillions of degrees above absolute zero, carried correlations in their decay products that can only be explained by a shared quantum state. Entanglement is woven into the most extreme processes the universe can produce. The universe has been non-local from the beginning. The universe you inhabit, at its foundation, is not made of separate things. It is made of correlations, of unified states spread across space, of quantum connections that disregard distance. The objects we see as distinct are patterns on the surface of something that has no interest in distinction at all. And if that is what entanglement means at the level of individual particles, imagine what it means when you apply it to observers, when you apply it to the people doing the measuring, because two physicists had already run the math on exactly that question. And what they found was that quantum mechanics does not merely produce strange results. Applied to the observers themselves, it produces a result that is logically impossible. In 2018, two theorists at a research institute in Zurich published a paper with a title that reads less like a scientific announcement and more like a verdict. Quantum theory cannot consistently describe the use of itself. Daniela Frauchiger and Renato Renner were not making a claim about experimental limitations or computational boundaries. They were claiming something structural. That quantum mechanics, applied carefully and correctly to a specific class of scenarios, produces an outright logical contradiction. Their scenario extended the Wigner's friend setup into 4 observers instead of 2, and the extension is where the logic breaks. Imagine 2 pairs of observers. 2 friends, call them F and F bar, are each sealed inside completely isolated laboratories. Each one measures a quantum particle, gets a definite result, and knows their own outcome. Then 2 super Wigners stand outside the labs. Each Wigner has the ability to perform a measurement on the entire sealed lab, including the friend inside, treating the whole thing as a quantum system in superposition. The scenario is carefully constructed so that certain predictions are guaranteed. F can calculate with certainty what the first Wigner will observe. F bar can calculate with certainty what the second will observe. These predictions use nothing but quantum mechanics, applied correctly to each observer's available information. So far, so consistent. The contradiction emerges when the 2 Wigners compare their results. The setup is engineered so that a specific combination of their outcomes implies, through standard logical transitivity, a conclusion that contradicts what both friends know they observed. The chain of reasoning is airtight at every link. Both friends' predictions are correct. Both Wigner's results follow directly from quantum mechanics. And yet, the combined statement produced by all four observers is simultaneously true and false. This is not a paradox in the popular sense, a puzzle that seems impossible but has a hidden resolution. It is a formal logical contradiction derived from the axioms of quantum mechanics itself. Voyager and Renner prove that quantum mechanics, if it applies to all physical systems without exception, produces inconsistent predictions when those systems include observers using quantum mechanics to reason about each other. Their conclusion: at least one of three foundational assumptions must be wrong. The first is universality, the idea that quantum mechanics applies to every physical system, including observers and measuring devices. The second is single world, the idea that each measurement produces exactly one outcome that the observer experiencing it can rely on as a fact. The third is consistency, the idea that one observer can use another observer's correctly derived conclusions as premises in their own reasoning. Every interpretation of quantum mechanics is forced to drop one. The Copenhagen interpretation saves itself by dropping universality. Quantum mechanics is just a calculation tool for predicting measurement outcomes, not a description of observers as physical systems. The many worlds interpretation drops single world. Every outcome happens, each in a different branch, and the contradiction only appears because different branches are being treated as if they share a common reality. Relational quantum mechanics drops consistency. Facts are real only for the observer who recorded them, and one observer cannot legitimately use another's facts as foundations for their own reasoning. Every exit requires dismembering something that felt fundamental. In 2025, a follow-up paper confirmed that any interpretation relying on subjective, observer-specific collapse fails to escape the contradiction. And the next question was whether the past itself could be tested. The answer is that the past is not what you think it is at all. John Archibald Wheeler was one of the most consequential physicists of the 20th century. He coined the term black hole. He worked with Niels Bohr on nuclear fission. He spent the last decades of his career asking questions that made his colleagues deeply uncomfortable because he was convinced that the implications of quantum mechanics reached further than the field had acknowledged. In 1978, he proposed what he called the delayed choice experiment. The setup begins with the standard double slit scenario. A quantum particle passes through two slits, and depending on whether a detector records which path it took, you get either a particle-like pattern or a wave-like interference pattern. Now, Wheeler asked a different question. What if you delay the decision of whether to measure the which path information until after the particle has already passed through the slits? The particle, by the time you make your measurement choice, has already crossed the screen. It should have already committed to being a wave or a particle. The choice of whether to look should come too late to matter. Wheeler's insight was that this expectation is wrong, and the experiments confirm it. If you choose to measure which path the particle took, you destroy the interference and get a particle-like result, even though the particle was already through the slits before you made that choice. If you choose not to measure, interference appears, and the particle retroactively behaved as a wave. The particle's nature at the moment of passing through the slits is determined by a measurement decision made afterward. This was done experimentally in France in 2007. By a team that used single photons and a delayed switching mechanism. The results matched Wheeler's prediction exactly. The photon passing through the apparatus behaved according to a choice made after it had already passed. Wheeler spent the rest of his life with a specific conclusion that he stated plainly and repeatedly: the past has no existence, except as it is recorded in the present. The history of a quantum system is constructed by the act of measurement, reaching back from the present into what we call the past and crystallizing a definite account out of what was, before the measurement, a multiplicity of possibilities. This is not a statement about imprecision in our knowledge. Wheeler was saying, based on the experimental evidence, that for quantum systems, there is no what happened prior to the measurement that determines it. The record written now is not a copy of something that already existed. It is the original. Wheeler proposed a cosmological version. Light from a distant quasar, gravitationally lensed around an intervening galaxy, takes two separate paths that converge on Earth. A detector can choose how to measure the arriving photons, either distinguishing the two paths or allowing them to interfere. The measurement choice is made on Earth when the photon arrives, but the photon left the quasar billions of years ago. The act of choosing how to measure today determines what path the photon took for that entire multi-billion-year journey. Every telescope, by pointing at distant objects and choosing how to measure their light, is participating in writing the universe's past. The past is not a completed record that we read. It is a record that we write backward through time as we observe. Wheeler died in 2008, still convinced that this was not a curiosity but a fundamental feature of the universe the field had not yet fully accepted. A year after his death, an experiment brought this logic one step closer to the undeniable. In 1999, a team of physicists at the University of Maryland built the delayed choice quantum eraser. The experiment is worth understanding in full detail because the mechanism is where the horror lives. A single photon passes through a double-slit screen. On the other side, a special crystal intercepts it and splits it into two entangled photons. One of them, called the signal photon, continues forward and strikes a detector screen. The other, called the idler photon, travels in the opposite direction toward a second set of detectors. The signal photon hits its screen first. Its position is recorded. Only then does the idler photon arrive at its detectors, where the experimental setup makes a choice: either preserve the witch path information, revealing which slit the original photon came through, or erase it, destroying the witch path record entirely. The signal photon's pattern on the screen appears random, individual hits scattered across the surface, forming no recognizable structure. But when the experimenters went back and sorted through the signal photon data, grouping each hit according to what the idler photon's detector registered afterward, the grouped subsets told a different story. The signal photons whose idler partners had their witch path information erased formed an interference pattern when their hits were recombined. The signal photons whose idler partners retained witch path information formed two blobs, like ordinary particles. The signal photon's behavior, determined at the moment it hit the screen, corresponded to a measurement made on its partner after the fact. The history of the signal photon was written by the future measurement of the idler. The physicist Yoon-Ho Kim led the team, and the results were published in the journal Physical Review Letters. They confirmed the prediction exactly. The story you can tell about the signal photon's past depends entirely on a choice made in its future. The past is not one thing. Before the idler measurement is made, both possible pasts exist simultaneously. The act of measurement collapses this multiplicity into a single history, but that history is chosen after the particle has already completed its journey. Paul Davies, reflecting on this experiment in 2025, described it this way: before the measurement is made, many pasts co-mingle in a kind of quantum superposition of histories. When a choice is made about what to measure, some of those histories are selected and others disappear. The remaining history is not discovered. It is chosen. If this seems like something that could be used to send signals backward in time, it cannot. The sorting operation that reveals the interference pattern requires classical information from the idler detector, which can only travel forward in time through ordinary channels. The retrocausality is real in the quantum description, but invisible to any single observer without that classical information in hand. The core finding stands. The past of a quantum system is genuinely undetermined until a measurement settles it, and that measurement can come after the particle has already arrived at its destination, after its history appears to have already been written. Wheeler was specifically interested in what this logic implies at cosmological distances, and he was not being metaphorical. He proposed a real experiment, physically realizable with existing technology, that would demonstrate the delayed choice principle across spans of space and time that dwarf anything a laboratory can stage. The setup uses gravitational lensing. When light from a very distant quasar passes near a massive galaxy on its way to Earth, the galaxy's gravity bends the light paths and creates multiple routes by which the photons can travel. Some routes pass around the left side of the galaxy, others around the right side. Both sets of routes arrive at Earth from slightly different angles, and both carry light from the same source. If you look carefully, you see two or more images of the same quasar because its light arrived via multiple paths. Now the measurement choice arrives. A telescope on Earth can be configured in one of two ways. The first way separates the two images, measuring them independently, asking which path each arriving photon took. The second configuration combines the two images interferometrically, allowing the light from both paths to overlap, asking whether the photon traveled both paths simultaneously. When the results are combined, interference effects appear. The quasar might be 10 billion light-years away. The lensing galaxy might be 5 billion light-years away. The photons striking the Earth-based telescope have been traveling for billions of years, and the choice of how to measure them when they arrive determines, retroactively, which path those photons took for their entire journey. Wheeler's language was precise. He said that by choosing how to measure arriving light, we are participating in the creation of the universe's past. The cosmos does not have a fixed history that exists independently of the observations made now. The history is assembled, progressively, by present observations reaching backward through time. This is not a claim about the limits of human knowledge. It is a claim about the structure of physical reality. The past exists as a defined set of events only where those events have been pinned down by measurements. Everywhere else, at every scale where quantum mechanics applies without decoherence fully settling the description, what we call the past is a superposition of possibilities that have not yet been selected. The universe, on this picture, is not a completed record being read. It is an ongoing process of record-making, in which every act of observation reaches backward and fills in history. The telescope looking at the lensed quasar is not just receiving old light. It is, in a technically precise sense, participating in determining where that light went for billions of years. If you are looking for a place where quantum mechanics stops being a problem about particles and starts being a problem about the nature of time itself, this is it. And the situation became considerably more alarming in 2012, when a mathematical proof removed the last comfortable place left to stand. For decades, the most popular way to stay calm about quantum mechanics was to treat the wave function as a kind of mathematical fiction. Physicists call this the epistemic view. The wave function does not represent anything physically real. It represents our knowledge, our state of information about a quantum system. When the wave function assigns a 50% probability to spin up and a 50% probability to spin down, it is not saying the particle is in a superposition of two physical realities. It is saying we do not know which way the spin is pointing because the spin already has a definite value and we simply have not checked. This view made quantum mechanics feel less disturbing. If the wave function is knowledge, not reality, then the collapse of the wave function when a measurement is made is not a physical event. It is an update. The same kind of update that happens when you flip a coin you had covered with your hand and then look. The coin was always heads or tails. You just did not know. The probability was in your head, not in the coin. If this were true, The strangeness of quantum mechanics would be a feature of our ignorance, not a feature of the world. The quantum realm would be weird in the way statistics is weird, a tool for managing uncertainty rather than a window onto a genuinely indefinite universe. In 2012, 3 physicists at the Perimeter Institute in Ontario published a mathematical proof that this view is wrong. Matthew Pusey, Jonathan Barrett, and Terry Rudolph derived what is now called the Pusey-Barrett-Rudolph theorem, and it is one of the most important results in quantum foundations in decades. The theorem addresses a specific question: is it possible for 2 different quantum states to correspond to the same underlying physical reality? If the wave function is just knowledge, then yes, different states of knowledge might describe the same physical situation. 2 physicists with different information about the same particle might assign it different wave functions, and both would describe the same underlying physical fact. Pusey, Barrett, and Rudolph proved that this possibility leads to a contradiction. If 2 distinct quantum states could correspond to the same physical reality, then quantum mechanics would predict certain measurement outcomes that are logically impossible. They derived, through careful mathematics, that preparing systems in certain quantum states and then measuring them in specific ways would force the measurement device to produce results that quantum mechanics assigns probability 0. The predictions would be self-refuting. The conclusion is stark. The wave function must be ontic, a word physicists use to mean physically real, corresponding to a genuine feature of the world, rather than a state of knowledge. The wave function is not a representation of your ignorance. It is a description of something that exists. The electron in superposition is not an electron with a hidden, definite spin that you happen not to know. It is an electron in a genuinely indefinite state, a state that does not resolve until measurement forces it to. Scott Aaronson, a leading computer scientist and quantum information theorist, titled his commentary on the result with 2 words: "Get real. The wave function is real. Deal with it." The implications began arriving immediately, because if the wave function is physically real, then an electron in the double slit experiment is genuinely physically passing through both slits at once. The interference is real interference between real physical structures spread across space. The collapse, when it happens, is a real physical event changing the actual state of the world. There is nothing under the surface that was already definite. This is the world, and the world was indefinite until measured. If the wave function is physically real, and the Schrödinger equation correctly describes how the wave function evolves over time, then a natural question follows with uncomfortable force. When exactly does the wave function collapse? The Schrödinger equation is linear and deterministic. It does not collapse. A wave function described by the Schrödinger equation continues spreading, continues evolving, continues existing in superposition without ever arriving at a single definite state. The equation has no mechanism for selecting one outcome. It describes a universe of ever-expanding, ever-entangling quantum superpositions, growing more complex with every interaction, branching in every direction, but never arriving at a definite single world. The collapse was always added as a separate rule. The Born rule, patched onto quantum mechanics by hand, because without it, the theory would not produce predictions that match what we observe. But the Born rule is not derived from the Schrödinger equation. It is an instruction imposed from outside the theory. And if the wave function is physically real, as the Pusey-Barrett-Rudolph theorem proves it must be, then a rule that modifies this physical reality, without any physical mechanism for doing so, is deeply suspect. Here is what follows if you take both claims seriously at once. The wave function is physically real, and the Schrödinger equation is always correct. There is no collapse. The wave function never narrows to a single outcome. Instead, every time a measurement is made, the measuring device becomes entangled with the measured system, and the combined wave function of both evolves to include all possible outcomes simultaneously. The observer who records the measurement becomes entangled with the device, and the observer's wave function evolves to include all possible observation results simultaneously. What we experience as getting one answer is what it feels like to be one branch of a superposition that has no ability to interact with its other branches. From inside any given branch, the world looks definite, classical, and single. From outside the system, from the perspective of the Schrödinger equation, every branch exists with equal reality. The exit door that said the wave function is just math is now locked from the outside. The theorem locks it. The wave function is real. The Schrödinger equation never fails. The only interpretation that can accommodate both of these facts without contradiction is one where the wave function never collapses. Every possible outcome of every measurement is equally real, and the universe you experience is one thread in a vast structure containing every thread at once. Consider what this implies about every quantum event that has ever occurred. Every radioactive decay since the Big Bang, every photon that bounced off a surface, every electron that jumped between energy levels, every chemical reaction in every organism that ever lived. For each of these events, the Schrödinger equation describes the universe branching into multiple superposed versions. None of those branches disappear. The equation does not include any mechanism for eliminating them. They accumulate at a rate that is incalculable in ordinary terms. This was the conclusion that Hugh Everett reached in 1957. He called it the theory of the universal wave function. The physics community spent decades trying to avoid it. After the Pusey-Barrett-Rudolph theorem, the avoidance became considerably harder. Hugh Everett was a doctoral student at Princeton when he wrote the thesis that would define his brief career in physics and haunt the field for the following 60 years. His advisor was John Wheeler, and Wheeler spent months softening the thesis before it could be submitted, concerned that the community was not ready for what Everett was saying. Everett's argument was simple in structure, if not in implication. The Schrödinger equation works. The wave function is real. Collapse is a fiction added to make the theory consistent with our experience. Remove the fiction, take the equation at face value, and you get a world where every possible quantum outcome occurs, each in its own branch of the universal wave function. The cat in the box is alive in one branch and dead in another, and both branches are equally real. When you open the box, you become entangled with the cat, and the version of you that finds a living cat is in one branch, while the version of you that finds a dead cat is in another. Both versions remember the same past up to the moment of opening the box. Both believe they are the one real observer. From inside each branch, the other branches are completely inaccessible. What we call the outcome of a measurement is what entanglement with a specific branch feels like from the inside. There is no preferred branch. There is no branch that is actually the real one. The universe contains all of them permanently, because the wave function that contains them all never collapses. Everett left physics shortly after submitting his thesis. The field had not been kind to his work. He went to work for the Department of Defense on nuclear war strategy and died in 1982 at 51, before the interpretation that bears his name became one of the most seriously discussed in quantum foundations, is now taken seriously by a significant fraction of physicists working on foundations. A 2025 survey of researchers in quantum foundations found it to be the second most common view after the Copenhagen adjacent position. Sean Carroll at the California Institute of Technology has argued publicly that many worlds is the only honest interpretation of quantum mechanics. David Deutsch has argued it is the only interpretation compatible with the way quantum computers actually work. What makes it terrifying is not its scientific plausibility. It is what it implies about you, specifically, and about everyone you know. Every quantum event branches the universe. Every radioactive decay. Every photon absorbed by a molecule. Every electron jumping between energy levels. Every chemical reaction in every neuron of every brain. The universe branches at a rate that is incomprehensible because the number of quantum events occurring in a gram of matter per second is incomprehensible. Every branch persists. None of them disappear. The wave function contains all of them simultaneously, spreading through a configuration space so vast that no human intuition can reach its edges. The branching has been happening since the first quantum events after the Big Bang. Every branch of every event has itself branched, and branched again, and continued branching in every direction simultaneously. The totality of existence on this picture is an incomprehensibly vast tree of equally real universes, each one internally consistent, each one populated by observers who believe they are in the only universe that exists, each one containing variations on every event that has ever occurred. There is a question at the heart of many worlds that physicists who take it seriously have not resolved in 60 years. And it is the question that makes the interpretation existentially, rather than just conceptually, troubling. When a measurement occurs and the universe branches into multiple copies, which one are you? The version of you that finds the particle spinning up, or the version that finds it spinning down? Both carry your memories up to that moment. Both believe they are the continuous person who existed before the branching. Both have every reasonable claim to being the real you. The question, which one am I, may simply have no answer, because both answers are equally correct. This matters because of what branching implies about survival. When people think about personal risk, they think in terms of probability. There is a 10% chance this will go badly. There is a 90% chance it will go fine. In many worlds, the question is different. The question is what fraction of your future branches will survive versus what fraction will not. If you step in front of traffic, the vast majority of your branches will be hit, and the vast majority will be severely harmed. A small number of branches will survive because of improbable quantum fluctuations in the microsecond before impact. All of those branches are equally real. All of those versions of you will proceed into their futures. The version of you reading this right now branched off from an enormous number of earlier moments where different outcomes were possible. Every version of you that survived past a dangerous moment has counterparts that did not. Those counterparts exist in other branches of the wave function, equally real, equally conscious, equally convinced they are the one true you. They are living different lives that diverged at some past branching point you never knew was happening. An infinite number of versions of you are facing catastrophic outcomes right now, in branches that split away from your current experience at some point in the past. The concept of "I survived" becomes incoherent. Some of your branches survived, others did not. And surviving means inhabiting one of the branches where the physics worked out. This is not a side effect of the many worlds interpretation that can be quietly managed. It is the central feature, and the branching does not occur only at the scale of human decisions or dramatic events. It occurs constantly, at the quantum level, at a rate that means the total number of branches of the universe doubles, and doubles, and doubles again, at speeds that make any attempt at counting meaningless. The universe is not a single history, it is all histories, simultaneously, equally, without distinction or preference. You are one thread in a fabric that contains every possible version of every possible event, and the fabric has been growing since the first instant after the beginning. What is stranger still is that this infinite branching structure is not the most disturbing conclusion quantum mechanics forces on you. There is a deeper layer that asks how the classical world you experience emerged from the quantum chaos underneath. The answer suggests that the solid reality around you is not the foundation but a shadow, a pattern that rose from deeper waters, selected by a process that looks uncomfortably like something we already know from the world of living things. Take the full weight of many worlds seriously for a moment, and a question appears that is almost more disturbing than the interpretation itself. If all branches are equally real, and each branch contains observers who see a definite classical world with definite outcomes, then where does that classical definiteness come from? Why does any branch look classical? Why does the universe, from inside any branch, look like a world of solid objects with definite properties, rather than a smear of quantum superpositions? The answer does not come from many worlds directly. It comes from a physicist named Wojciech Zurek, working at Los Alamos National Laboratory, who has spent decades building a framework he calls quantum Darwinism. And what quantum Darwinism reveals about the nature of classical reality is, depending on your tolerance for vertigo, either the most beautiful or the most alarming idea in modern physics. Decoherence explains part of the story. When a quantum system interacts with its environment, the countless air molecules, photons, and vibrations entangle with the system, and the quantum coherence that allows superposition leaks away into the environment faster than any instrument can track. The quantum behavior does not disappear. It becomes distributed across so many particles that it is effectively invisible from any local perspective. But decoherence does not explain why multiple observers agree about what they see. For that, you need quantum Darwinism. Here is Zurek's insight. Observers never measure quantum systems directly. They intercept fragments of the environment that has interacted with the system. When you see a chair, you are intercepting photons that bounced off it, a small sample of the flood of environmental particles that interacted with it a moment ago. What you measure is an environmental fragment carrying information about the chair. Only certain quantum states of the chair leave redundant imprints across many independent environmental fragments simultaneously. Zurek calls these pointer states. The same information about the chair is encoded in thousands of separate photons, each accessible to a different observer. This redundancy is why multiple observers, sampling different fragments, agree about what they see. Only the states robust enough to broadcast their information widely survive as classically accessible facts. The rest decohere into invisibility. Classical reality is the evolutionary winner. Zurek's own words from 2025 are worth quoting. The solid and objective reality we all believe exists is a construct, devised by our consciousness, and based on second-hand information eavesdropped by us from the environment. The chair is real in the sense that information about it is encoded in the environment. But it is not fundamental. It is a survivor. Solidity is not the ground floor of reality. It is an outcome of a selection process built into the structure of quantum mechanics itself. A 2025 mathematical proof by Zurek and his colleague Bin Yan confirmed this more rigorously. Observers accessing independent environmental fragments must reach the same conclusion about the pointer state of a system. Classical consensus is mathematically guaranteed as long as the observers are truly outside the system, but the proof has a condition that quietly unravels everything it seemed to promise, and that condition is where the next layer of the horror lives. There is an experiment that has been haunting quantum mechanics since 1993 because it demonstrates something that should be logically impossible. You can gain information about an object without ever physically interacting with it. And the mechanism by which this works reveals something deeply disturbing about the nature of the paths that go untaken. Imagine you have a collection of bombs. Some of them live and some of them duds. The live bombs are triggered by a single photon touching the sensor. One photon. That is all it takes. The dud bombs have non-functional sensors that do not respond to photons at all. Your task is to identify which bombs are live and which are duds, without detonating a single live bomb. Classically, this is impossible. The only test available is to touch the sensor with a photon. If the bomb is live, it explodes. You cannot discover its nature without triggering it. Two physicists, Avshalom Elitzur and Lev Weidman, found a quantum solution in their 1993 paper. Build an interferometer that splits a photon along two paths and recombines them. Tune it so that, with no obstruction, all photons exit toward one detector due to complete destructive interference at the recombination point. The second detector never fires. That is guaranteed by the wave nature of light. Now, place a live bomb in one of the two paths. Three outcomes are possible. The photon hits the sensor and detonates the bomb. The photon reaches the intended detector as normal, or the photon reaches the second detector, which should never happen. That third outcome is everything. The second detector fires only when the interferometer has been disturbed. If the photon reaches it, the photon must have traveled the path away from the bomb. The bomb sensor was never touched. The bomb never detonated. Yet the second detector firing tells you, with certainty, that the bomb is live. Knowledge of the bomb was obtained without any photon ever reaching it. Elitzur and Weidman called this interaction-free measurement. A team led by Paul Kwiat refined the technique in 1995 using the quantum Zeno effect, demonstrating that with repeated partial measurements, you can identify live bombs with near-perfect efficiency, while detonating almost none of them. The mechanism works because the photon's wave function explored both paths simultaneously. The bomb's presence in one path changed the global interference conditions, affecting the behavior of the photon even on the path it never physically traveled. The path not taken exerted a real, measurable, physical influence on the outcome. This is the deepest implication of quantum mechanics applied to physical possibilities. The universe does not compute only the path a particle actually takes. It computes every path the particle could have taken, and the results of those unactualized possibilities feed back into what actually happens. Counterfactuals have causal force. What did not happen shapes what did. In many worlds' terms, this follows directly. The other path is real in another branch, and the interference is the consequence of those branches interacting before they fully separate. The bomb that did not explode here is a bomb that exploded in another equally real branch. The path not taken in your world was taken in another, and its shadow reached across to shape what you experienced. The universe is not a sequence of events moving forward along a single track. It is a computation that evaluates every possibility simultaneously. And what you experience is what that computation returned for your particular thread of the wave function. There is no branch that is more real than the others. Which means the question of what you are and what it means for you to agree about a shared reality with anyone else becomes something the math alone cannot answer. And it turns out the math has something specific to say about why you agree at all. There is a question at the center of many worlds that no one has cleanly resolved in the 60 years since Everett wrote it down, and it is the question that makes the whole framework existentially rather than just conceptually disturbing. When a measurement happens, and the universe splits into multiple branches, which one are you? The branch where the particle spun up, or the branch where it spun down? Both versions of you emerged from the same moment. Both carry identical memories of everything before the branching. Both believe without question that they are the single continuous person who existed a moment earlier. Both are correct. The question, which one am I, may be entirely incoherent because the answer is both and always has been. There is no fact of the matter about which version is the real one. The wave function makes no distinction. Both versions are real threads in a physically real structure, and both proceed into their futures with equal claim to being you. This reframes every question about personal survival. When people think about risk, they think in terms of probability. 10% chance something goes wrong, 90% chance it goes fine. In many worlds, that frame dissolves. What you are actually asking is, what fraction of my future branches will still exist an hour from now? Both sets of future. You are experiencing their situations as vividly as you experience this moment. Think about every dangerous moment you have ever passed through. Every time a car came close. Every illness that resolved. All of those alternative outcomes were physically realized. There are branches where versions of you, identical to you up to that moment, encountered the worst outcome and have been living differently ever since. They exist right now. They are fully real. The concept of "I survived" loses its footing. What happened is that both sets of branches continued. The version of you here, reading this, is one of the branches that made it through. Whether that version is more real than any other is a question the wave function treats with complete indifference. And this branching is not happening only during dramatic events. It is happening constantly, at every quantum interaction, in every atom of your body, at a rate that generates new branches faster than any number can track. Every neuron firing in your brain involves quantum-scale chemistry. Every photon your eyes absorb is a quantum event that branches the universe. Every breath, every heartbeat, every thought unfolds across a constantly expanding structure of parallel realities, each one inhabited by a version of you who has no idea the others exist. The identity problem has no solution that lets you rest easy. Stand back far enough to see the full shape of what many worlds implies, and the scale becomes difficult to hold in mind without something giving way. The branching did not start with the first human observation. It started with the first quantum event after the Big Bang, nearly 14 billion years ago. Every quantum interaction since that moment has branched the universe. Every radioactive decay in every dying star, every photon absorbed by every molecule in every planetary atmosphere, every electron transition in every atom of every element ever forged in stellar cores. Each of those events split the wave function of the entire universe into multiple threads. None of those threads were eliminated. They all persisted, and each one has been branching again ever since. The number of branches that currently exist is not a number anyone can responsibly write down. It exceeds by an incomprehensible margin the number of atoms in the observable universe. The total configuration space the wave function occupies is so vast that it makes the observable universe look like a single point. Each branch is internally coherent. Each contains observers who experience a definite classical world with solid objects, definite histories, and a single consistent past. Each contains people having conversations, making decisions, forming memories, and constructing science. None of those branches knows about the others, because the branches cannot interact once they have diverged beyond a certain point. The quantum coherence that would allow interference decoheres almost instantly at the scales where observers exist. From inside any branch, the universe looks singular and unambiguous. Every version of every event that was quantum mechanically possible has been realized, written permanently into the structure of reality itself. Every outcome you narrowly avoided continued forward in a branch just as real as yours. The many worlds interpretation does not predict this as an interesting side consequence. It requires it. If the Schrödinger equation is universally valid and the wave function is physically real, as Pusey, Barrett, and Rudolph proved it must be, then the branching is not a philosophical flourish. It is as physically real as the ground beneath your feet. Every possibility is a physical fact. This is the scale at which the horror of quantum mechanics operates. The universe is not a story proceeding along a single timeline. It is the sum of all possible stories, all of them playing out simultaneously, all of them equally real, none of them having any special claim to being the one that actually happened. What you experience as the world is what one thread in that vast structure looks like from the inside. And somehow, from inside that incomprehensible quantum superposition, You experience a world of chairs and tables and definite events and shared facts, and two people can stand in a room and agree about what they see. The question of how that agreement is possible has an answer. The answer is beautiful and deeply unsettling in equal measure. Every classical object you have ever seen, you have seen indirectly. When you look at a chair, you are not measuring the chair. You are intercepting photons that bounced off it, photons that represent a tiny sample of the vast flood of environmental particles that have interacted with the chair in the past instant. The air molecules that bounced off its surface, the infrared radiation it emitted, the vibrations it transmitted to the floor. Each of those particles carried away information about the chair's state. What you access when you see it is one small fragment of that environmental record. Physicist Wojciech Surek recognized that this is not just a practical limitation. It is the key to understanding why multiple observers agree about what they see, despite living inside a quantum universe that should dissolve all definite properties the moment you look away. His framework, which he calls quantum Darwinism, explains how classical reality emerges from quantum mechanics through a process that looks remarkably like natural selection. When a quantum system interacts with its environment, only certain quantum states are stable enough to leave the same imprint across many independent environmental fragments simultaneously. These are what Surek calls pointer states. The chair's position and shape are pointer states. Information about where the chair is gets encoded redundantly into thousands of separate photons, each accessible to a different observer. Any observer who intercepts any one of those photons reads the same answer. This is why multiple people in the same room agree. States that are not pointer states do not survive. Fragile quantum superpositions decohere almost instantly because they cannot maintain redundant imprints across the environment. They are selected against, in exactly the Darwinian sense. The environment acts as a filter, passing only the robust, redundantly encoded states into the realm of shared classical fact. Classical reality is not the ground floor. It is the winner of a competition. The solid world you experience is made up of quantum states robust enough to broadcast their information into the environment widely enough that everyone checking gets the same answer. Surek himself, writing in 2025, put it plainly: the solid and objective reality we all believe exists is a construct, built from second-hand information eavesdropped from the environment, and the consensus between observers reflects the redundancy of that information, not the existence of an independently definite world beneath. A mathematical proof published by Surek and his colleague Bin Yan in 2025 confirmed this more rigorously than ever before. Observers who access genuinely independent fragments of a quantum system's environment are mathematically guaranteed to reach the same conclusion. Classical agreement between observers is not an assumption or a social convention. It is a theorem derived from quantum mechanics itself. This sounds like solid ground. Here is a mathematical guarantee. The world you see is the world everyone else sees. But read the condition. The theorem applies when observers are accessing genuinely independent fragments of the environment. It applies when observers are outside the system. Look at what happens when that condition breaks. Imagine you have a collection of bombs, some live and some inert. Each live bomb carries a sensor so sensitive that a single photon touching it causes detonation. The inert bombs have sensors that do not respond. Your task is to identify which bombs are live without triggering any of them. Classically, this is logically impossible. The only available test involves touching the sensor with a photon. If the bomb is live, the test itself destroys it. Physicists Avshalom Elitzur and Lev Weidman published their solution in 1993, and it works by exploiting something that has no classical analog: the physical reality of paths not taken. Build a device that splits a photon into two paths, redirects both paths with mirrors, and recombines them at a second beam splitter. Tune the device carefully so that when nothing interferes with either path, the photon always exits toward detector 1 and detector 2 never fires. This is guaranteed by destructive interference. With a clear apparatus, detector 2 is silent by the laws of physics. Now, place a live bomb in one of the two paths. The bomb's sensor is a detector. Its presence makes the which path information available, which destroys the interference condition. With interference broken, detector 2 can fire. Three things can now happen. The photon enters the path where the bomb sits and detonates it. The photon enters the other path and exits at detector 1 as usual, or the photon exits at detector 2. That third outcome changes everything. Detector 2 firing means the interferometer was disturbed. The photon took the path away from the bomb. The bomb's sensor was never touched. The bomb did not explode. But detector 2 only fires when something is present in the other path. The fact that it fired is proof the bomb is live. Knowledge of the bomb arrived without any photon ever reaching it. Paul Kwiat and his collaborators extended this in 1995 using the quantum Zeno effect, chaining together repeated partial measurements to drive the efficiency near 100%. Subsequent experiments with trapped atoms confirmed interaction-free measurement in physical systems. The effect is real and reproducible. The mechanism that makes it work is the wave function exploring both paths simultaneously. The bomb's presence in one path affected the global interference conditions across both paths, including the path where no photon arrived. The unactualized possibility of reaching the bomb had real, measurable consequences for what happened on the path that was taken. The counterfactual was causally active. In the many worlds picture, this is not mysterious. Both paths are real in different branches. The interference between branches, before they fully separate, shapes the outcome you observe. The path not taken in your experience was taken in another equally real branch, and the shadow of that branch fell across yours and changed what happened. The universe computes every possibility, and the results shape the single outcome you experience. At the largest scales available in experiments built around particle colliders, this principle has now been put to the test in ways that push the strangeness further than any thought experiment could. The quantum experiments of the early 20th century were, by necessity, small, individual electrons, single photons, atoms in carefully cooled vacuum chambers. The effects were delicate and easily destroyed by heat and vibration, which made it tempting to believe that quantum behavior was a feature of the very small, that entanglement and superposition dissolved at any scale approaching the everyday. For decades, this belief shaped how physicists talked about their field. In 2024, two experiments at the Large Hadron Collider disposed of this belief in the most emphatic way available. The two collaborations operating the massive particle detectors at the collider outside Geneva, the two independent detector collaborations, announced the observation of quantum entanglement between top quarks and their antiparticles. The top quark is the heaviest fundamental particle known to physics, more than 170 times the mass of a proton. It is produced in the most violent particle collisions humans have ever achieved, at energies corresponding to temperatures trillions of degrees above absolute zero. It exists for less than a trillionth of a second before decaying, a lifetime so brief it ends before there is any time to interact with surroundings and lose quantum coherence through decoherence. Despite all of this, both teams measured correlations in the spin states of top quarks and their antiparticles that can only be explained by a shared quantum state. The quarks were produced together with spins correlated in ways that violate any classical explanation. The entanglement was not measured directly in the quarks themselves, which decay too fast to probe individually, but in the angular distribution of their decay products, the W bosons and bottom quarks that spray outward when the top quarks disintegrate. Those angular distributions carried the unmistakable statistical signature of a prior entangled state. preserved even after the entangled particles themselves had ceased to exist. The implication strikes at a belief that made quantum mechanics easier to live with. If quantum effects were safely confined to the very small, then the paradoxes and contradictions could be treated as features of an alien microscopic realm, interesting to physicists and irrelevant to the macroscopic world, where observers, measurements, and reality actually function. These results close this escape route. Quantum entanglement operates inside the most extreme processes the universe produces. There is no energy scale, no temperature, no level of violence that strips the universe of its quantum character. If entanglement is woven into the most extreme particle processes, the next question follows with inescapable logic. What if the geometry of the universe itself is a quantum object, subject to superposition and entanglement, and all of the paradoxes that come with them? The experiments attempting to answer that question are already under construction. In 2025, a team published a paper in the New Journal of Physics that described an experiment pushing the Wigner's friend scenario closer to a human observer than any previous attempt had managed. Instead of using photon systems as stand-ins for the friend observer inside the sealed laboratory, the team used an artificial intelligence system, one capable of learning from new data, updating its internal representations, and producing outputs that bore increasing structural resemblance to the inferences a human observer would make. The researchers framed it as the first step of a long-term program: progressively replace the photon-based stand-in with more sophisticated systems. At each stage, testing whether observer-independent facts reappear. A photon pair has no inner life, no persistent memory, no capacity to reason, so perhaps the violations found in earlier experiments reflect only that the observers were not really observers. Perhaps when the system inside the laboratory is complex enough, objective facts re-emerge. They tested a specific set of inequalities called local friendliness inequalities, derived from the work of Czeslaw Bruckner and his collaborators. These inequalities are stronger than Bell inequalities. Violating them requires that the friend, observer inside the lab has both a definite local experience and the capacity to communicate information about that experience to the outside. The system was designed to satisfy both criteria at increasing levels of sophistication across successive experimental runs. The physical setup preserved the essential paradox structure. Inside the sealed region, the system processed quantum measurement data, formed an internal representation of the outcome it had detected, and encoded that representation in its state. The external Wigner observers then measured the sealed region as a whole, treating the system and the particle together as a single quantum object. The system could not communicate its result to Wigner without disturbing the quantum state his measurement was probing. The structure held two observers, each applying quantum mechanics correctly to their own accessible information, each arriving at an account of events that could not be combined into one coherent picture. The violations grew larger, not smaller, as the system became more capable. The more closely the internal observer resembled something like a genuine observer, one capable of learning, of forming a representation of the experimental outcome, of producing a coherent output about what it had found, the more clearly the experiment confirmed that its perspective and Wigner's external perspective were irreconcilable. Observer-independent facts became harder to defend as the observer became more like the kind of thing we usually mean when we say observer. The research program is ongoing. Its designers expect to work progressively toward human-like observers over coming years, at each stage asking whether the boundary at which objective reality re-emerges has finally been found. Every step so far has found no boundary. The horror of Wigner's friend does not weaken as the friend becomes more like you. If the trend holds, the paradox does not dissolve when confronted with minds. It deepens, and if observer independence fails even as the observer approaches human complexity, the question of where it could possibly hold steady leads directly to the largest canvas available. the fabric of space-time itself. Physicists Sugato Bose, Anupam Mazumdar, and Vlatko Vedral worked independently in 2017 to propose an experiment that would determine whether gravity, the force that shapes the largest structures in the universe, is fundamentally quantum. Their proposal has a logic to it that is almost painfully direct. Quantum theory requires that if two systems interact, and at least one is quantum, the interaction can generate entanglement. If two massive objects become entangled through gravity alone, the interaction must have been mediated by a quantum process. Gravity must be a quantum force. And if gravity is quantum, then space-time, which is what gravity is in Einstein's general theory of relativity, is also a quantum object, subject to superposition and branching. Like everything else, the Schrödinger equation governs. The experiment requires placing two small masses into quantum superposition simultaneously, allowing only gravity to act between them, and then measuring whether entanglement develops in their positions. If entanglement appears, the only possible mediator is gravity, and it must have operated as a quantum channel. The engineering challenge is severe. Any vibration, any stray electromagnetic field, any uncontrolled interaction with the environment will destroy the fragile quantum superpositions before gravity has time to act. Multiple groups in Europe and the United States are now attempting to solve this with tabletop setups using nanomechanical oscillators and magnetically levitated microspheres. The difficulty is that gravity is extraordinarily weak compared to every other known force. The electromagnetic force between two small objects at the separations needed for the experiment is trillions of times stronger than the gravitational attraction. Eliminating every stray electromagnetic influence while maintaining quantum coherence in both masses requires experimental control that has never been achieved for objects heavy enough to exert measurable gravitational pull on each other. The theoretical groundwork has been confirmed. A 2023 paper by a large collaboration including Chiara Marletto, Vlatko Vedral, Lejos Diosi, Czaslaw Bruckner, Carlo Rovelli, and colleagues, published in Physical Review Letters, demonstrated that entanglement generated by locally mediated gravity is consistent with the standard framework of linearized quantum gravity. The physics requires no exotic new assumptions. The engineering simply has not caught up. But consider what confirmation would mean. If space-time is a quantum object, two possible curvatures of space can be simultaneously real, just as two spin states of an electron are simultaneously real before measurement. The very sequence in which events occur can be in superposition. The shape of the universe around you is subject to quantum uncertainty. Every paradox that applies to a particle in a box now applies to the box itself. Observer-independent facts about the curvature of space become as contested as observer-independent facts about a photon's polarization. The branching of the wave function includes branches with different geometries, different space-time structures, each one equally real. This is the frontier where quantum mechanics is heading, and standing between that frontier and complete conceptual dissolution is a theorem that, for a brief moment, offers solid ground. A paper submitted to the Public Physics Archive on the 22nd of March 2025 by Wojciech Zurek and Bin Yan at Los Alamos National Laboratory proved something that physicists had long assumed but never rigorously established: the mathematical reason why multiple observers agree about reality. The theorem starts from quantum mechanics without additional assumptions. It considers multiple observers, each one accessing a separate fragment of the environment that has interacted with a quantum system. The environment acts as a channel through which information about the system is broadcast, and each observer samples a different portion of that broadcast. The theorem proves that any set of observers accessing genuinely independent, non-overlapping fragments must reach the same conclusion about the system's pointer state. Their agreements are not coincidences. They are mathematical inevitabilities. The proof works by showing that the redundancy of the pointer state's environmental imprint forces all independently sampled fragments to encode the same information. Two people looking at a rock from across a room are sampling different photons, different environmental fragments, but because the rock's position is a pointer state, both fragments encode the same answer. The consensus is not a coincidence or a social agreement. It is a mathematical necessity. The reason two people looking at the same rock see the same rock is not the reliability of human perception or the rock existing objectively in space. It is the consequence of a quantum mechanical selection process. Only the states robust enough to broadcast redundant information across the environment survive into shared experience. Classical agreement between observers is a theorem. The shared world you inhabit has a mathematical foundation. The word pointer state carries a specific technical meaning. A pointer state is a quantum state that remains stable against interaction with the environment, one that does not get randomized into new superpositions by the thermal noise of the surrounding world. The position of a rock is a pointer state. The spin state of a single electron, delicately prepared in a laboratory, is not. A stable state can interact with thousands of environmental particles and imprint the same information on each one. An unstable superposition decoheres rapidly, and no single fragment can recover it. The theorem guarantees agreement because pointer states are the only ones that survive the selection pressure of environmental interaction. For a moment, this feels like the solid ground the entire subject has been missing. After chapter of escalating dread, here is a result that says the reason reality feels real is derivable. Quantum mechanics itself guarantees that independent observers agree. Hold the theorem carefully. The condition is not a minor technical footnote. It is the entire structure on which the comfort rests. And when you examine what it actually says, the solid ground gives way completely. The theorem's condition is precise. Observers must be accessing genuinely independent fragments of the environment. They must be outside the quantum system whose state they are measuring. They must be sampling different portions of the environmental broadcast rather than accessing the system's internal quantum state directly. When these conditions are met, the theorem holds. Classical consensus is guaranteed. Multiple observers agree. Now look at the scenarios where the theorem does not apply. Look at the Wigner's friend experiment. The friend inside the sealed laboratory measures the particle directly, accessing its internal quantum state. She is inside the system, she is part of the system. From Wigner's external perspective, she and the particle and the measuring device are all components of a single quantum system that he describes with a wave function. The theorem says nothing about this case. The mathematical guarantee of consensus applies to observers outside the system, sampling independent environmental fragments. It does not apply to observers who are inside the system. And in every Wigner's friend scenario, every nested observer scenario, every situation where a quantum system includes observers who are themselves quantum systems being observed from outside, the theorem is silent. The consensus it guarantees does not exist. The moment an observer becomes the observed, the moment the measurement is made by something that is itself a part of the quantum system being measured, the mathematical basis for agreement dissolves. The pointer states that would allow consensus require environmental broadcasting. When the observer is inside the system, there is no outside environment to broadcast into. The observer's measurement is an internal quantum event, and the Wigner watching from outside can describe the entire interior as still in superposition, still undetermined, still containing the observer's definite result only as one component of an unresolved quantum state. The Zurek-Yan theorem makes classical reality mathematically secure at every scale where you are truly external to what you measure. It makes it mathematically absent at every scale where you are not. Think about what that means for you. The vast majority of your observations are external. You see objects that have been interacting with the environment, and the theorem protects your consensus with the world in all of those cases. But you are also a physical system. Your brain is made of atoms following quantum mechanical rules. From the perspective of a hypothetical super-observer with access to the complete quantum state of everything, you are inside the system. Your internal state, your definite sense of having perceived something specific, is part of a larger wave function that this super-observer describes without any definite outcome for you. Your certainty about your own experience is not a fact the theorem can protect, and increasingly, as experiments push further toward placing observers inside quantum systems, the boundary where observer independence should reappear remains invisible. The consensus that feels so natural in everyday life is supported only for as long as you remain outside the box. The moment the box includes you, the theorem no longer applies, and the mathematics that makes the world feel solid simply stops working. Every path forward from here leads through a door. There are exactly 3 of them. None of them open onto anything comfortable. Every serious attempt to make peace with quantum mechanics eventually arrives at the same 3 exits. Physicists have known about them for decades. Each one has been explored in depth, defended by serious thinkers, and subjected to devastating philosophical pressure. None of them survive without surrendering something that once seemed non-negotiable about the nature of reality. The first exit is the one most physicists take in practice, even if they rarely say so out loud. Sometimes called Copenhagen, its essential move is to treat quantum mechanics as a prediction machine rather than a description of reality. The wave function is a tool for calculating probabilities. The question of what really happens between measurements is not a scientific question. Physics tells you what you will observe, not what exists. The unsettling implication. The most successful theory in the history of physics is not in the business of describing the world. It is in the business of updating your expectations. Science becomes a very powerful form of bookkeeping, and the universe behind the books is declared off-limits to inquiry. This position saves you from every horror described so far, because none of the horrors arise if the wave function is merely mathematical. The trouble is that the Pusey-Barrett-Rudolph theorem closes this exit from the outside. The proof established that the wave function must be physically real. If you take the Copenhagen position after 2012, you are taking it in direct conflict with a published mathematical proof. The door is still there, but the structural supports have been removed. The second exit is many worlds. Take the Schrödinger equation seriously. Take the theorem seriously. Let the wave function evolve without ever collapsing. Every outcome of every measurement is realized in a different branch of the physically real wave function. The apparent collapse you experience is what entanglement with a specific branch feels like from the inside. The math is clean, the logic is consistent, and the price is that everything is real. Every branch, every version of every event, every version of you. An infinite structure of equally real universes, branching constantly, never converging, growing without limit. The third exit searches for new physics, some undiscovered mechanism that introduces genuine collapse without branching. Something beyond the Schrödinger equation that selects one outcome without requiring all others to persist. This exit is blocked from 2 directions simultaneously. The theorem requires any new theory to still include a physically real wave function. The Froude-Renner paradox requires any consistent extension of quantum mechanics to either abandon universality or permit multiple outcomes. Every proposed solution to the measurement problem over the past 50 years has been caught between these 2 constraints. There is no fourth door. There is no interpretation that returns you to the intuitive classical world, the world of definite values, observer-independent facts, singular histories, and solid objects whose properties exist whether or not anyone is looking. That world was always a projection. It emerged from quantum mechanics through decoherence and environmental selection, real enough for practical purposes, but built on a foundation that never included the classical solidity it appeared to offer. All 3 of them, from a sufficient distance, look like the same thing. A universe that does not commit to being anything specific until it absolutely must. Return to the beginning, A darkened room, a screen on one wall, a source firing electrons one at a time toward a barrier with two narrow slits. One electron travels. It arrives. A tiny dot of light appears on the screen. And then another and another, each one seemingly random, each one definite. Nothing suspicious, just a particle hitting a screen. But keep watching. Dot after dot after dot accumulates. An hour passes, and the dots arrange themselves not into two bands, as you would expect if each electron passed through one slit or the other, but into an interference pattern, bright stripes and dark stripes. Each electron, fired alone, interfered with itself. It passed through both slits simultaneously. Its wave function spread across both openings, and the two paths met on the other side, cancelling in some places and reinforcing in others. That pattern on the screen is where this entire journey started. It is also where it ends, because everything you now know reframes what that pattern is. Every dot on that screen is a moment of observation collapsing a physically real wave function into a definite outcome. Every dot is a universe branching into every possible landing point, with your branch being the one where the electron arrived at this exact location, and all the other branches equally real, equally occupied by a version of you watching their own dot land somewhere else. The wave function carries all of them forward, impartially, without distinction. Every choice of whether to place a detector at the slits reaches back and determines what path the electron will have had. With no detector, the electron's history is a wave spreading through both paths. With a detector, the electron's history is a single path. The history does not precede the observation. The observation writes the history, reaching backward to the moment the electron left the source, crystallizing a definite account from what was, before the measurement, a superposition of every possible trajectory. The electrons that built that pattern are entangled with the measuring devices that recorded them, which are entangled with the observers who read the devices, and the chain extends outward through the universe without any natural stopping point, because the Heisenberg cut has no location and the wave function contains no instruction for ending any branch it creates. The double slit experiment was never about electrons. It was a message, written in interference fringes, about what reality is made of. It waited in darkened laboratories while the physics community developed the tools to read it. Bell proved the universe had no hidden depths. Wigner's friend proved the message applies to observers. The Pusey-Barrett-Rudolph theorem proved it describes something physically real. The Frauschiger-Renner paradox proved the theory cannot even consistently describe itself. The message became stranger as understanding grew. That is the one consistent feature of the entire investigation. Every time physicists found a way to understand quantum mechanics better, the understanding made the situation worse. The screen is still there. The pattern is still building. Reality is still waiting for someone to look. That waiting is what matter does, including the matter that makes up a mind in a darkened room, building a picture of the universe one dot at a time, and finding that every dot is also building a picture of the mind, doing the looking. The observation and the observed were never separate. They have been the same process, folded back on itself, since the first quantum event after the beginning of everything. And it took 90 years of physics to confirm what one interference pattern was already showing to anyone willing to sit in the dark long enough to see it.